Okay, for question 3.81. Before we solve this question, there's an important concept that I feel that we should go over. So, the concept goes this way. If you have a force acting here, a force acting here, and the distance r, we are told that from our previous classes, we are already told that through the principle of transmissibility that a force can be made to act at any point along a straight line and to have the same effect. But if we want to move this force to another point, let's say to this point O, to this origin here, we cannot move it arbitrarily, right? So for us to move this force from here to this place, we have to follow another methodology, which is very important to this question that we're going to solve. So the first thing we are going to do, if you want to transfer this force, is that you have a force here. So for this origin, what we're going to do is we are going to draw another force here, and because we already know that when you have uh, two forces of same magnitude and which are acting in opposite direction, they are going to have the they are going to have an equivalent, like the resultant force on the body will be zero, right? Because they're acting in different directions with the same force, right? So it means that this first body is equivalent to this other body, right? So now, if we notice something, we can see that this initial F here and this negative F here, it forms a couple, right? Here. So we have so because of this, because we have F here and negative F here, and there's R, the distance between them, you can simply represent this again with this. It simply means that you can write out this force here, and you can now replace this F and minus F here with a moment here. So M. So what we are saying here is that, and this is point O, right? It means that we have been able to move our force F from this point to this point. So we have this force F now here. But the only difference here is that we are taking into account the moment about this force. The moment here, we have represented it here. So you can simply write it out like this. OR is equivalent to at O. Then you have to know that it has to be perpendicular. So M and F. But you also have to know that this M here, this M that we wrote here, is the moment acting about this point. That means it is the moment here. So this is a very important concept that we are going to use to solve these types of questions. So that concept is very important. So let's move into our question proper. So here we are told that 500 Newton force here is applied to a bent plate as shown. So we are told to determine an equivalent force couple system at point B and an equivalent system formed by vertical force A and a force as B. So let's take it one by one. Let's solve A first. So we want to replace this 500 Newton force by an equivalent force couple system at B. So let's draw out our free body diagram this way. So initially we have a force 500 here, Now we want to move it to this point. So an equivalent force curve system at B. We have B, A, A, B. So we are moving this force. So according to our system here, if you want to move this from here to here, you can simply replace it by drawing this force here and a moment. But we also have to note that these moments that is written here will now be the moment about this initial point. So we are going to have a force and this moment about this point. So let's go into our calculations. So to get this our so let's first convert our force to vector form. So that will be, you know, the magnitude of our force is 500, right? So we want to convert it. So that will be F vector form to be 500. Also note that here I told that this is 30 degrees, but because to make our calculation easier, can just take the the angle to the horizontal, which is 60 degrees. So I'm going to use 60 degrees for our calculation. That will be 500 cos 60 I minus 500 sine 60 I. And if you notice here that one is positive and the other one is negative. So from our initial classes, we know that if we resolve this into horizontal and vertical components like this, we have an initial force here, and this is Fy and this is Fx. So we are now going to consider the way it is going to move our body. So if you have an horizontal force pushing this body this way, like this Fx this way, so which way is it going to move? So we can see that if you have a force pushing this, and if this is a rigid body, right, pushing it, we see that our body will tend to move in an anti-clockwise direction. So we're not going to expatiate on that because we have discussed that before. So we can see that it's going to move in an anti-clockwise direction. And like we said, for moment, anti-clockwise is always positive. So that is why our 500 cos 60 is positive. And for our Fy, you can see that if a force is pushing our body here, down here, you see that it will tend to move our body in a clockwise direction. So, and clockwise for moment is negative. So that is why our 500 sine 60 is negative. So we expand this, get 250 I minus 433J. That's our F. So, like we said, what we are looking for here is our M, right? So we want to calculate this our M, so we can replace this force here by another force at B. So the formula for our F, as always, is RF. So we still need to find our R. So like we said here, that when we are replacing this force, this moment is the moment about the initial, when we are replacing this force here by another force at another point and by the moment, so to form a couple, you can say that that moment is actually the moment of the moment about that initial, this point to this point. So it means that our R is going to be directed towards the initial point. So like for this, the distance of our r will be directed towards this point. So it's going to be directed towards the initial force. So this is going to be our initial point, and this is going to be our final point. So we have to move from this place, from this point B to the initial point of application of our force. Like we said before, there are two methods that we can use to get our points. So we are going to use one of them here. So we are going to travel along XYZ. So we are at point B here, and we want to move to this initial point here. On the x-axis, we are going to travel this distance. And we're already given the distance in millimeter, which is 300 millimeter. So we are writing it in meter. So that would be 0.3 I. And because we are moving along the x-axis, natural x-axis is going to be positive. Then when we get to this point, we have to move along the y-axis. So we have to move downwards. So that is going to be negative, right? So that will be minus. Then what's the distance that we're moving? What's the magnitude of distance we're moving? We're moving down 175 millimeter. And that is going to be 0.175. So 0.175 G. So since we now have our R and we have our F, we can calculate our moments. So we just write our IJK same way, then we input our values 0.3 minus 0.175 and 0, right? And our F 250 minus 433 and 0. So we can see by observation that for our I, we cross this out and multiply. Since we have 0 on the two parts, the coefficient of our I is going to be 0. And same thing with our G when we resolve it. Then for our K, so we are going to have value for only K only. So we expand that, it will be 0.3 into minus 433, then minus, then 250 minus 0.175. So expanding that, we should have minus 129.9 plus 43.75. Then we're going to have minus 86.15 Newton meter, right? So that is simply our moment. And as you can see that it is negative, so it means it is clockwise. And it means that our equivalent force couple system at B, according to this our image here, will be this way. It means that we're going to have A, B. So we're going to have a force at B, which is going to have a magnitude of 500, same as this force that I moved. Then the moment about this point is going to be, M is going to be equivalent to minus 86.15 Newton meter. So this is the equivalent couple system at B. So when we move, so let's move to the other part of the question, which is question B. And here we are told that we should determine an equivalent system formed by a vertical force at A and a force at point B. So what we are simply to do is that, so A and B, we're going to have a force here, basically vertical force another force at B. Like we said again, we are going to use the same methodology. If you have a force at B, which you want to move to points, if you have a force here, which you want to move, what we have to take note of first is our moment, right? So we need to get the moment about this point. And like we already calculated from here, we can see that the moment at this point B here, from this point B here is 86.15. You can simply use that same value to get our force, right? Since we know that this same this same force here, to write it here, right? The moment about this point is equivalent. So we can simply bring back our value here, the magnitude of m, and if you get the magnitude of m from that point, so like from here is m is magnitude of m is simply 86.15 Newton meter. So bring out this 86.15 here is equal to the same force times distance here. Let's look at this. If you want to do it at the same point, the same force, when we have a force at A, you take a moment about this B in this other direction, you can see that it's simply going to be this force A times the distance between points A and B, right? So we're just going to write out our force A times the distance between A and B, which we're already given here as 125 mm. So I'm going to write that as 0.125. So you can calculate our FA as 86.15 over 0.125, which is going to give us 689.2 Newton. So also here, and we also need to know that the resultant of our forces, when we want to replace a force with another, with two forces, like in this case, the resultant of these two forces must give us the initial force. So you can say the resultant of FA plus FB should be equal to our R, and the resultant here is the initial force that we have, that is the 500 in vector form. So our R, consider it that as, from our initial calculation, it is 250I minus 433J. If for some reason 689J. Then our FA 689.2J. So let's find our FB, which is the other force at B. It's going to be, from this formula, it's going to be R minus FA. That will be simply 250I minus 433J, then minus 689.2J. So our FB will just be 250I minus 1122.23J. You can just find the magnitude of our FB, which will just give us 1149.7 Newton. So we can also calculate the direction of our FB, and that can give us, direction is simply arctan, the y component and x component. That will be 1 arctan 1 2 2.23 over 250, which will give us 77.4 degrees. So to summarize our answer, if you are to replace an equivalent system formed by a vertical force at F and a force at B, we simply be the vertical force at F, which you can write as FE, simply be 689 Newton, magnitude there, 689 Newton, and our FB be 1150 Newton, in direction of 27.4 degrees. With that, we have solved the question in full.